Some of our homework last night was on page 467, 1 to 13. There's 4 questions that have been requested here, so we'll go over those 4, 6, 7b, 10, and 13, starting with question number 6, which says, great question, I love this question. It says, using the concept of impulse, explain how a karate expert can break a board. Impulse, you remember, is defined as the change in momentum. And the equation for impulse is going to be relevant here, even though we're not going to actually use it to solve a mathematical problem. It's going to be relevant for us in determining the kind of the concept behind how this karate expert would break this board. The equation for impulse, remember from your data sheet, is F times delta T is equal to M times delta V, but we usually stick that delta P in front of it to remind us of what that equation actually is. The first thought that I had when I read this question the first time, without doing karate, I don't do karate or any kind of martial arts myself, so I don't know, I've never known the technique of doing it. But the first thought that came to my mind was, well, okay, you're going to hit the board as hard as you can, and you're going to want to try to minimize the time of contact, which is going to maximize the force, right? That makes sense, right? What's the problem with that? What's the problem with that rationale behind breaking a board? Trying to maximize the force there. Sorry? Yeah, you're going to break your hand as well, right? Okay, because if you apply a force on the board, certain value, then the board's going to apply an equal and opposite force back on you of the same value, which means that probably if it's going to break your hand, maybe it ends up breaking if it's going to break the board, maybe it ends up breaking your hand as well. So you don't actually want to try to minimize the time to maximize the force. That's not the way you do it. Rather, what you do, if you have a board sticking out like this, is visualize a point behind the board. And this is what karate people will say, is that you visualize a point behind the board, and then you try to hit that point behind the board. See what I'm talking about here? So there's an imaginary point behind the board here, and you're trying to hit that point behind the board. What does that cause you to do? Yeah, it causes you to basically follow through there, right? Which increases the time interval. Why would you want to increase the time interval? Doesn't that minimize the force? No, what you want to do is start the board moving. And when you start the board moving, what you want to do is maximize the impulse. And how do you maximize the impulse? Hit it hard, apply a big force. But what do you also do? Increase the time of contact. In other words, follow through. Just like when you try to hit the golf ball really, really far, really, really fast, you want to not only hit it hard, you want to maximize the time of contact to increase the impulse. So that's what you do when you're breaking a board. Not try to minimize the time to maximize the force, but rather you want to try to whack it hard and maximize the time to maximize the impulse on the board. In other words, get the board moving, okay, which will ultimately cause it to break if the board vibrates enough. Does that make sense? Anybody have an answer that was kind of like that? Okay, a couple of you did. Yeah, good. That's a tough question, actually. If you're not a karate person, that's a particularly tough question, right? If you already know the technique, then it becomes easier to explain it using impulse if you know the technique, even if you didn't know the physics behind it, right? If you're not a karate person, you don't know the technique, then that's a really, really challenging question. Okay, next question we have is number 7. Somebody asked, who asked me for 7B? Who was it asked? Dawson, what'd you get for 7A? You know what, let's just do the whole thing, okay? Anybody else get that? 2250? Okay. We'll go over the whole thing here. Right away, we want to find the impulse there. That's fine, because when I see that graph, 3 words should come to my mind, right? What are those 3 words? I think I heard somebody say, I don't know. Not those 3 words. No. Impulse equals area, area equals impulse, right? 3 words, area equals impulse. We see this graph, force versus time, area equals impulse. Now, you do have to be careful here that we have milliseconds on the bottom here, right? So we got to convert that to seconds, which is 10 to the minus 3. Let's find the area or the impulse. We're going to find that by saying, in this case, 1/2 base times height, because it is a triangle. The base here goes from, what is that, 0.5 to 5.5. So the base would be 5 times 10 to the minus 3, because it's milliseconds. And my height is 900 newtons. Dawson, I think what you might have done there is forgotten to convert to seconds there, eh? Okay. So let's say 0.5 times 5 times 10 to the minus 3 times 900. What does that work out to be? Who's got that so I don't have to pull out my calculator and get it? Not 2,000, I don't think. 2.25? If you got 2,000, then I think what's happened is you forgot to convert that to seconds, right? You've just used a base of 5 as opposed to 5 times 10 to the minus 3. So my units here, of course, are newton seconds, or we could say kilograms meters per second because we're talking about impulse. There's the answer to A. Now the answer to B, what's the velocity of the ball when the racket and the ball separate? Remember, there's one other thing that we can do with these problems involving force versus time graphs, and that is to set the impulse equal to m times delta v. But you guys know, of course, that's my only other option. I'm not going to set it equal to F times t because the force is changing. Got to stick with m times delta v. Look, I already know the impulse. It's the area. So let's set that equal to 2.25. The mass here given to me is 48 grams, or 0.048 kilograms. And then we multiply that by delta V. If I divide 2.25 divided by 0.048, I get 46.875. That's my change in velocity. Now, does it say it started from rest? Yeah, it was served, so we can assume that it starts at rest. That means if it starts at rest, my final velocity that I'm looking for would be exactly the same as my change in velocity, right? If I go from 0 to 46, my change is 46, but my final is also 46. Ryan, did you have a question there? No? We'd round this probably to 46.9 meters per second. It's pretty fast, right? That's why I don't play tennis. Not because I can't serve it that fast, and I can't, but because I don't want to be served to that fast. If I saw a tennis ball coming at me at 50 meters per second, which is somewhere in the range of 180 kilometers per hour, I just get out of the way, as opposed to try to hit it back, because I'd have no hope. How many people got that 46.9? Okay, good. And number 10 was our next question. Says an advertisement for a battery-powered 25 kilogram skateboard says it can carry an 80 kilogram person at a speed of 8.5 meters per second. Sounds kind of dangerous to me. The skateboard motor can exert a net force of 75 newtons. How long will it take to attain that speed? When we see force and time, how long will it take? Force and time in the same questions, we think impulse, just like we thought those three words, area equals impulse for the graph. So let's say F times T is equal to M times delta V. Let's rearrange this to solve for T this time. What do we get for mass here? Oh, interesting. Interesting. What do we use for mass? If assuming there's a person on it, I don't think it actually says that. Like, it says it can carry a person of 80 kilograms. Let's assume, for purposes of this question, that there is an 80 kilogram person on it. The total mass that we'd use would be 105 kilograms. Anybody use 25 kilograms? I don't think it's really clear here. I don't think they're really clear on whether the person is on it or not. It can carry it, but it doesn't say how long would it take to attain the speed if there is a person on it. I'm going to assume that there is. I think that's what they mean, but we don't really know for sure. Delta V is VF minus VI, which is final minus initial, or we got, what, 8.5 minus 0, divided by my force here, which is going to be 75 newtons. And what do we get when we do that? 105 times 8.5. Times 8.5, and then let's divide that by 75. Look at that. 0 to 8.5 meters per second in 11.9 seconds or 12 seconds. Okay, so this is not something that you probably want to race a race car in because A, it doesn't go very fast, and B, it doesn't accelerate very quickly. But it is a skateboard. Good. And our last question, number 13, says experienced curlers, that's a good one. Experienced curlers know how to safely stop a moving stone. What do they do and why? Who's a curler here? Anybody curl? Nobody? We got like 3 or 4 in the other class. Anybody ever watch curling? Yeah, some of you. Listen, this is pathetic. More of you watch curling than baseball. Uh, then I had a little thing at the beginning of the year. We were talking about baseball and physics and momentum, and asked who watches baseball, and nobody watches baseball. You watch baseball? Oh, come on. I guess you came to the right class, at least. Um, if you watch curling, maybe you've noticed how sometimes they stop a curling rock. Curling rocks are 20 kilograms, which means they're almost 50 pounds. That's heavy. That's about the same mass as one of those big 20-liter water jugs that you put on the water coolers. You can imagine having one of those water jugs full of water coming at you at several meters per second. When you've got something with that amount of momentum, it's going to, we know that it's going to come to a stop. If it stops quickly, then the force is going to be large. And if that force is provided by you, it's going to hurt. Now, the impulse of that curling stone is predetermined. It's going to stop. We don't know how it's going to stop. Maybe it's going to stop because you stick your foot in front of it. Maybe it's going to stop because it hits the wall of the rink. And maybe it's going to stop because of something else that you do. But the impulse is going to be predetermined. What you want to do is maximize the stopping time of that curling rock to reduce the force. Just like the airbag, just like the baseball glove, just like the helmet, and just like it's like the straws around the egg that we did last week, right? Maximize the stopping time, minimize the force. So how do you do that? Well, there's a number of ways. I'm not a curler, but I think if you had a rock that was moving slowly, you could put your foot in front of it and then kind of just move your foot back with it, kind of cradle it like that. Sometimes I see people using their broom to kind of cradle it. Right, here's the rock coming slowly, and they just kind of cradle it back like this to increase the stopping time. It's going really fast, then I would suggest probably the smartest thing to do is just let it go and hit the wall and let the wall take the damage as opposed to your foot. Bottom line is anything that you can do to increase the stopping time is going to decrease the force. Okay, make sense? Okay.